live. Okay, probably you can hear me, huh? Okay.
Yes, sir, I can hear you.
Okay, thank you. So let me make this class, let's share the screen. In the last class, we discussed about denoising. Today's class is some application specific topic. And in this era of pandemic, this particular thing has gained a very important or crucial role in our daily life. Usually, before COVID, usually all the household and we are the common people, they do not use these pulse oximeters. But nowadays, because of COVID, we usually, many of us, they actually keep this kind of thing in our house so that during the requirement we can use it. So it is not that because of COVID it is been included here. It is there in the in your syllabus, this biomedical instrumentation, and now you can feel the real importance of knowing at least the basic of these things. If you do not know the basic, then what are the ways, what are the different things that we must be careful of? Otherwise we can have a say a wrong interpretation of the result. And it happens in many cases. The people are quite happy with the oxygen saturation level measured at house, and when they are brought to the hospital or to the doctor with the very good instruments, there is something different. Why that difference happens, that we can have the understanding of that after going through the principle. So you will see that calibration is very important in this kind of instruments. So over time, if it is not recalibrated, over the time, the accuracy of the measurement may vary. So that is why this kind of a thing, what is the basic principle, you can have the idea from this particular topic. And one more thing, nowadays, uh, this kind of wearable or portable devices, portable biomedical devices or health monitoring devices, they have a very good market. If you can come up with a solution which is pretty much accurate and quite handy to use, then that can have a very good market to sell. As this is a professional course, and as you are in the fourth year, this kind of things you must be knowing, and you must be aware of these things. Nowadays, probably because of Shark Tank, most of you are thinking of being an entrepreneur. That okay, the urge was already there from long ago, but nowadays, because of all these programs and others, it has become a very what we can say, it is amplified. So many of the young students, and they want to become young entrepreneurs. That's good. So this kind of a biomedical instrumentation is one of the very booming sector. Wearable accessory means like this one I have given. Say this is an Apple or smartwatch, and it can also monitor. What is the principle and what kind of a modification you can incorporate to do a new thing. So this kind of a thing you can have the idea with this. Okay. So probably you have seen the Shark Tank, huh?
Yes, sir.
Okay. Even if you don't see in your Facebook or other feeds those memes and other things, they will come, I am sure. Okay. So here, this is one particular thing that you can think of. Okay. You can have one feature like this one, and you can add so many features with it, and you can have a good product to sell. See the pulse oximeter. So let's start. So pulse oximeter, and we are interested in the measurement part. And the pulse oximeter actually measures the oxygen saturation. You have heard the term oxygen saturation, but anyone, do you have idea what does it really mean? What is the meaning of the oxygen saturation? From common sense, from your class 9, 10 biology class knowledge.
Amount of oxygen that is carried by the blood.
Yes, and who is actually carrying the oxygen in the blood?
The hemoglobin.
Hemoglobin, yes. So hemoglobin, the oxygen molecules can be attached to the hemoglobin, that will make it the oxyhemoglobin. And then the carbon dioxide also can be attached to it, because in the deoxygenated blood and simple only oxygen hemoglobin can be there. We have to measure what is the oxygen saturation level, and it should be high. If it is not high, then that means it indicates either your lung or heart is not operating properly. That means they are the main reasons of introducing the external oxygen to the blood and extracting out the carbon dioxide that produced by the body and put into the blood with the help of the hemoglobins. Okay, so we don't have to be a doctor to just know these things. Okay, so whatever I have explained, maybe in medical term, there can be, those terms can be wrong, but from engineering aspect, we are not interested in those medical terms. We are going to learn what is the technical challenge and how to solve it. So here you have seen, this is the basic diagram, this is the basic photograph of it. And here the fingers have to be inserted, and it is the cross-sectional view of that. And you can think of, at the top cover, there exists a light source. And you may think that there is only one single light source. They seem to be, but it is not actually. There are two different LEDs are there for two different wavelengths. And there is a photo detector. It detects the different wavelengths passing through the finger, and there exists some analysis tool or processor, and processor is programmed to do some calculations, and the thing is shown. Whatever I have shown here in the right side, here, can you see any difference between what is shown here in the diagram and here? Can you identify any difference? It is not only the percentage. No, percentage value I am not talking about.
So beats per minute.
Yes. Here you can see two things. One is SpO2, that is the thing, and other is the rate of heartbeat. Okay. So these two things are shown. Here it is only one, because our actual aim is to measure the oxygen saturation, but we can say, I'll explain that additionally, if you want to measure this SpO2, additionally, you will get the information of the pulse rate or the heart rate. Okay. Why is it so? We'll explain. And this is another, I have already shown, this is another variety of that. Nowadays, this kind of an instrument is not there. Now, very sophisticated and costly equipments are already in the market, and you can wear it like a watch, and it is a smart watch. And also your fitness gear, you can call it, and it will measure all of your body parameters, not only the SpO2 or heart rate. There are so many things it can measure. So how and in which way, considering the cost of the gear, cost of the accessories, you can implement so many things there. So here we are discussing about only the pulse oximetry, but there is an enormous opportunity so that you can modify this kind of available things into a quite a new one. So basic idea is from the basic chemistry, or we can say the property of say hemoglobin and blood. The oxygenated hemoglobin or oxygen saturation in the blood, that has a relationship, basic relationship with the partial pressure of the oxygen. You know that if the partial pressure increases, that means it is going to be saturated. That means if a particular region is saturated with, say, water vapor, that means your partial pressure of that water vapor should increase with the increase in the saturation. At, say, 100% saturation, the partial pressure will be maximum, and that is called the SVP, saturation vapor pressure. So here also the partial pressure of oxygen has a relationship with the oxygen saturation. Obviously that should be, but it is not a linear one. So what, and also the partial pressure measurement directly, that requires an invasive way. So you have to put some probe inside the blood stream and then you can measure. So without those invasive method, because for biomedical thing, we do not prefer invasive methods. Okay. Nowadays, even blood sugar monitoring, that requires pricking of the skin. A needle has to be inserted through the skin to take the blood. So nowadays, people are thinking of even bypassing that, because whatever, if you are making that system invasive for biomedical, there is a question of security. So that is why we usually don't prefer that. So that is why pulse oximetry is a non-invasive technique. So we have to measure this one. And how? See, I told you that we can have the blood hemoglobin. It is connected to oxygen, that is called the oxyhemoglobin, and also say carbon dioxide and some variety of that can be attached to the blood hemoglobin. We are not talking about that. We are considering, say, this HB hemoglobin and HbO2. So what are they? Actually, what we are talking about here, y-axis is the absorption coefficient and x-axis is the wavelength. So what is the basic idea? Basic idea is that if we pass some wavelength, light of some wavelength through our body, our hemoglobin will absorb some amount of light. Okay, let me put it a bit easier. So that means if we are passing a light through our fingers, then some portion of the light will be absorbed by our body. Now within the body, who will absorb that? Majority of the absorption will be done by those muscles and other things, and also by the blood. In blood, the majority of the absorption will be done by hemoglobin and HbO2. Here, that absorption at different wavelength, you can think that at different wavelength, they are not same, like your black body radiation, and it is also true for absorption, that all of the wavelengths are not absorbed in equal intensity. So here different wavelengths are absorbed with different intensities, and at this point it is approximately 805 nanometer. 805 nanometer, experimentally it has been found that 805 nanometer HbO2 and your hemoglobin, they are having almost same absorption coefficient. So that can be used as a reference that how much oxygen is there. So if the oxygen is not there, so therefore absorption of that particular wavelength will be low. So how much light is being absorbed, depending upon that we can identify how much oxygen is there. So in the first diagram that I have shown here, so the amount of light that is passing through the photodetector, that actually gives how much amount of oxygen is there in the blood. That is the basic principle. But as I have said this, you can readily identify or readily you can think of, if you are at all listening to, then there are some very common question that may arise. For example, if there is a thin person and a fat person, okay, so if the finger is thin, then the path is small, so amount of light passing through may be of high intensity. If the finger thickness is more, then maybe automatically the light intensity will be reduced. So how to take care of that? That maybe the two person, they are having same SpO2, but one has a very thin finger, other has having thick finger. So the intensity will automatically go down. So how to take care of that? And also there are other things, that means whenever say some heart pumping and other things occurs, so there will be some change in the blood flow. So how to take care of that, or how to use that kind of a change into our measurement? So first of all, let us discuss about that. Usually the two wavelengths are chosen, one where they are actually having small difference or low difference. Sometimes it is close to this 900 something nanometer, and other is here near about say 600, where this HB and this HbO2, they are having quite a different absorption coefficient, okay, to segregate them. So that is why two wavelengths are there, because to eliminate those inter subject variability, because for some person the finger may be thick, some person finger may be thin. So that is why at two different wavelengths for the same person, we can have the measurement. It is shown there. Usually it is measured either 805 or 940 nanometer, and the other one is as a 660 nanometer, because 940 or 805, they are almost having the same absorption coefficient, and at 660 they are having the maximum difference in the absorption coefficient between oxygenated hemoglobin and deoxygenated hemoglobin. Up to this, if you have any question, you can ask. Up to this. No question. Okay, very good. So in your illumination course, maybe you have heard this Beer-Lambert law, and that is giving you, say, a light, incident light, that is I suffix I, and it is passing through some object, and the object is absorbing some amount of light, and after absorption the light is emitted from this is, say, T, I transmitted light intensity. So that relation from experimental validation, it has been found that this relationship is sort of an exponential, that is IT is I into e to the power minus something. E to the power minus something, you know, the curve actually looks like an exponentially decaying curve. So here IT is the transmitted light, I is the incident light, A is the absorption coefficient, C is the concentration of absorbing material, that is C is our the point of interest here. That means actually we are trying to find out SpO2, that means oxygen saturation, and that depends on the this concentration, that means HbO2, the concentration of HbO2, that is actually given by this one. And D is the length of the path, that means the thickness of the path. So here, if we take log on both the sides, you can understand, if we take log, so it will be only ACD. So this particular AC into D is called the optical density. Okay, it is called the optical density. So if we have this optical density, there is an empirical formula that is, it is something A minus B by OD1 by OD2. What is OD1? It is optical density at wavelength 1, say that is 904, 940 nanometer, or OD2 is the at say 660 nanometer. Okay, at two different wavelengths, if we just perform it, we can find out this SO2. Why? Let us discuss it in more detail. So OD1 at say one particular wavelength. At one particular wavelength, your OD1 is say ACD for your oxygenated blood, plus ACD for this for the reduced oxygenated blood or hemoglobin. So O for oxygenated hemoglobin and R for reduced or deoxygenated hemoglobin. Okay, so A means absorption coefficient of your HbO2, CO is the concentration of HbO2, D is the path. That means it is say some blood vessel thickness. Similarly, AR1 is the absorption coefficient of reduced or deoxygenated blood at wavelength 1. CR is the concentration of that hemoglobin and D is the thickness. You can see these two Ds are same. Why? Because they are actually oxygenated hemoglobin and deoxygenated hemoglobin, they are actually within the blood vessel. So therefore blood vessel thickness D, they are same. Now what is there apart from the blood vessel? Some tissue, muscles, etc. So those AX1 is the absorption coefficient of that tissue. CX is the concentration of that. DX is the thickness of that. Similarly, OD2, I have just told you that we have to, that instrument actually measures this OD for two different wavelengths to compare. Now, if we take differential of that, so what is that? That means you can understand only the last term vanishes. Why the last term vanishes? Because absorption coefficient, concentration, they won't change much. But because of the blood condition, say for some reason, this average CO is constant. But what happens is that whenever the heart is pumped, this D, the thickness of the blood vessel, they changes. The thickness changes. Why? Because whenever the heart is pumped, the blood vessel, they are actually, because of the inrush of current, inrush of blood current, then what happens is that their diameter increases. So D increases. But as in terms of your total thickness, that dx compared to D is much larger. So therefore dx will not get changed. So if we take differential, so there won't be any change of dx. So delta dx is 0. So that is why the last term we can eliminate. And this is the, if we take the difference of this OD1, that means optical density at wavelength 1, say for 660 nanometer. If the instrument takes some time, that actually waits for the change in OD1. So change in OD1, that can be represented at this. So delta D is the change of the volume of the or thickness of the blood vessels because of the heart pumping blood or heart taking out the blood from that particular portion, because of the periodic pushing and or compressing and expansion of the heart. Okay. Now tell me, what is the problem here now?
স্যার ওই পালসটা কত পালস আছে ওটা জাস্ট ডায়ামিটারের ডিফারেন্স দেখেই ক্যালকুলেশনটা হয়
না, ডায়ামিটারের ডিফারেন্স তো কেউ মাপতে পারে না। যেটা মাপতে পারে সেটা হচ্ছে যে ফর ওডি1টা কতটা ভ্যারি করছে, পার সেকেন্ডে বা পার মিনিটে কতবার চেঞ্জ হলো, এটা বুঝতে পেরেছো?
আচ্ছা, ওটা দিয়ে পালসটা
Exactly. ওই intensity per minute কতটা করে চেঞ্জ করছে for a particular element, because pulse rate তো same. So OD1 and delta OD2 should, or sorry, OD1 and OD2 that has the same number of intensity changes in 1 minute. It will not wait for 1 minute, it will wait for 4-5 seconds, and within 4-5 seconds how many times it has been changing. On the basis of that it will show you.
Okay, sir.
Because delta D, there is no such thickness measuring device. It is only by measuring the intensity of light. All the mathematical jugglery is done on the basis of this intensity measurement. Okay. So here R is a new term we are just telling, that is delta OD1 by delta OD2. This OD1 and OD2, they are actually measured from the intensity, and the chip inside that actually calculates this. And what is the saturation? Oxygen saturation, that is oxygenated blood concentration, oxygenated hemoglobin concentration divided by CO plus reduced total hemoglobin concentration. So this is actually the SpO2 that we are trying to find out. So here R we can measure from material property. From material property we can have the idea of, say, absorption coefficient and others, and concentrations are like this. So AO1, AR1, AO2, AR2, they are known, they are material property. That means what is the absorption coefficient of oxygenated hemoglobin HbO2 for wavelength 1, that is known from the graph. So A0, A1, AR1, AO2, AR2, they are actually known. And this is the quantity that we are trying to find out. So how to solve it? R we can measure. So from this equation, so here from this equation 1, if I write it as equation 1, from equation 1 we find out, say, value of CR. Find out value of CR as the function of R and CO, and the other coefficients will be A01. So put this CR value here, put this CR here, and solve it. You will find the value. You can solve it of your own, and you will find it is like this. It is coming up as this one. So in this equation, what are the things that your instrument measures? In this equation, what are the things your instrument measures?
Only R, sir.
Only R. Very good. Only R, and we are trying to find out this. It measures R, and all those parameters are known. So just put this and you can calculate. But this is one commonly used formula. There are different sources of error, you can understand that. Okay, because all those variations and others, and this particular thing, that variation of dx we have considered negligible, it can have an effect. So okay, it is not always that much straightforward as it is written, but it is quite acceptable formula that is used. But there is a ample scope of improvement of this one. So you can have your own algorithm and you can make a better instrument. So that is why there are different types of instruments, different, so low cost, high cost. If your instruments take care of so many things, so many factors, then all those calculations, measurement, that is been incorporated, and that is why the cost will become high. So there are different instruments, and they requires frequent calibration and say maintenance. Because if, say, your photo detector, after, say, you are keeping that in at your home, and say some dust and other things is being deposited on the photo detector, so the intensity will automatically be low, so you will not get the true reading. So that is why different types of thing, that because with time the LED you are using, with time their intensity that may get varied. So therefore it is very difficult. If that particular intensity is already low, then the calibration may not be proper. So there are so many things, so many sources of error that can be there. So that should be taken care of. I am just giving you the idea. There are n number of ways, and this is the schematic, not the photograph, the schematic of this one. So there are two LEDs, and at certain frequency they are actually sending, and this they are the LEDs, and this is the photodiode. This is the receiver. So if the light intensity is more, the photodiode current will be more. Here you can see we are using one logarithmic amplifier. Why it is logarithmic amplifier? What does it mean? Logarithmic amplifier. That means if your input is say Vi, some voltage is Vi, your output Vo will be some log function of this input voltage. Okay, that is the with some multiplying factor K. So logarithmic amplifier, if we give some input Vi, so your V output will be proportional to log of this Vi. Okay, clear? Now tell me, why is it so? Why this logarithmic amplifier is required? So what kind of amplifier you are going to use, that actually dependent upon the basic principle of your system. Why there is log amplifier required? Because of this thing, because of this calculation. We are actually find out this OD, optical density, and that is log of the ratio of the intensities. So that is why, and the ratio of intensities is actually indicated by the voltage. Voltage is actually proportional to the photodiode current. Photodiode current is dependent on the intensity. That is why we have to take the log of that voltage. Okay. বলো এটা কি বুঝতে পারলে? কনিষ্ক?
Sir, has
তোমরা ঘুমোচ্ছ নাকি?
No, sir.
ঘুমোচ্ছ না রে? এ কেমন যাদবপুরের স্টুডেন্ট, সকালবেলা 10টার সময় ঘুমোই না? এরকম যাদবপুরের স্টুডেন্ট তো কখনো দেখা যায়নি। যাদবপুরে তুমি ইঞ্জিনিয়ারিং ফ্যাকাল্টিতে পড়ো, অথচ 10টার সময় তুমি একদম পুরো সচেতন জেগে বসে আছো, ক্লাস করছো। হাউ ইজ ইট পসিবল? Now, if your society doesn't accept you, is it the fault of the society? সোসাইটি এখন যদি তোমাকে অ্যাকসেপ্ট না করে, যে না যাদবপুরে পড়ছো ইঞ্জিনিয়ারিং ফ্যাকাল্টিতে 10টার সময় জেগে গেছে, এই তো তাহলে হতেই পারে না। সেটা কি সোসাইটির ফল্ট না তোমাদের, বলো তো? ওকে, there are two different modes. One that I have shown, that is very commonly used, that is your LED is at the top and the photodiode is at the bottom, so the light is passing through the finger. That is, it is called the transmission type. Okay, that means it is a transmission type, and other is reflection type. I have shown you that smartwatch, the smartwatch is there, so your source, light source is at the top, as well as your photo receptor is also on the top. So that means the light that is reflected from this bloods and tissues, they are actually reaching via this part. So one that is I have shown, that is very common, that is light is being passing through the finger, and other light is actually being reflected from the source and reaching the receptor. Okay.
Sir, how are we getting the ratio, sir? Like,
Sorry, just a minute. I have drawn the diagram wrongly. Here, this is the source. This is the source. This is the source, and light is being reflected there from here. And from another LED, it is here, like this. Yes. Now your question.
I understood, sir. That was mistake. I understood.
So this is the light. This is lambda 1. So now actually the microcontroller or the processor, it is actually controlled that at this time we are sending lambda 1. what is the intensity reached here. So that is your, it is taking the log of that, and it is calculating, say, this OD1. And here it is also, say, for lambda 2. Now, when it is sending wavelength lambda 2, then the intensity obtained, it is calculating as OD2, like that. And in weights, and it actually records the variation, how many times it is varying. So from that, it can actually find out what is the pulse rate. Okay. Bolo. And you can also use the logarithmic amplifier. The logarithmic amplifier, because it can make our scale linear, because the relationship is, say, non-linear, exponential for that IT and I. So here we can use this kind of an amplifier. That means it is a very common your feedback amplifier using op amp. Here this portion is wrong. This will be minus, this will be plus. Those who are not attending the class or looking just in the exam, they will copy the class notes. Those mistakes will just make them identified. Okay, just correct it in your note. So this should be minus, this should be plus. So here you know that for a diode, the voltage versus current, this is the current, voltage versus current has an exponential relation. So here, this is the current of that particular, say, if we use the diode, and this is the voltage from the photodiode. Okay, this is the voltage, and this voltage you can think of as this is 0 volt. So this is 0 volt again, because for the virtual ground. So this is the 0 volt, and no current can pass through this op amp. So no current can pass through because of the infinite impedance. So the I, that current is passing through the diode, that will be passed through this one. So V in by R in, so you can think of this V in by R in is the current. And this current, this EO, this current has a, this EO is the voltage across the diode. This E output, this is the voltage across the diode. So this EO has a relationship with this of the current, like this one. So that means what will be the value of EO? See, this is your I. I is the current, and this is the V in by R in. So R is the constant. So therefore V in is dependent on I. It is dependent on I. So therefore this EO will be log of this V in, because EO is the voltage across the diode. So EO will be have some relationship log to this current I. So log to the current I is basically log to this voltage. So in this way we can implement the log amplifier. You can also use the transistor, or you can use the diode, and using this kind of a logarithmic amplifier you can have it. Now, what are the different sources of our contribution? What are the new things you can add? See, all these characteristics, you can use a transistor also, like this one. So the problem is here, the curve, this one, this should be a linear one. Otherwise, it is very difficult for that particular algorithm to judge what is the oxygen saturation. If it is the nonlinear, then there will be so many points you have to check, and in the lookup table you have to store it. So how many things, what are the things you can do? See here. Here we are using only a very simple calculation. We are calculation, say this is R, we are calculating this R, and we are just taking this log, and yet as we are taking the log, we are assuming that the relationship is, say, it is sort of a, say, linear relationship. That means, but actually, in reality, that particular equation may not be exactly exponential. Maybe something like this. This may not be some constant. This particular e to the power minus thing, it is not actually only one exponential. It can be sum of very different exponentials. Okay. So those kind of accuracy you can add. Moreover, in that particular phase, we have assumed that, say, the dx, that means thickness of all the tissues and others, they are fairly constant. You can also introduce something to take care of that. These are some thinking topic regarding this. You can add your contribution there to make this particular thing much more effective. So as it is actually comparing the two wavelengths, so the subject-wise variability that can be eliminated. Okay, now tell me your question on this. Anything that you want to ask? Bolo. So nowadays, people are also trying to add, say, blood sugar monitoring and other things. Okay, they are actually finding whether any other wavelength or something that has something to some relationship with the blood sugar. So from that, they can also find out the blood sugar. Usually with the watch, there exists, like mobile phone, there exists accelerometers. So if you are working, jogging or something, working out, then how many times the steps, if you put one step, there exists some vibration. So from the vibration, how many times in 1 minute you are just doing that. From that, it is calculating how many calories you are burning. So this kind of smartwatch, they are actually building on that particular algorithm. So you can add on so many things: SpO2, pulse rate, and now it is they're also proposing ECG monitoring. I do not know how much they are accurate, but it can be. Tell me if you have any queries. Okay, for my part, that is pretty easy, and as well as not much of the time that will take. I'll take this from 10 to 11 class every week, so that will be sufficient for me to complete the syllabus. So for today, I should stop here, because next topic I can start, but that is not required.